They're not known for having a high amount of torque. I guess they're kind of similar to rotaries in that regard.
Oh, you just triggered a whole bunch of people right there.
I know.
On this episode of Tuned In, we've got Craig Williams from Neutron Engines joining us. And Craig is a pretty smart cookie when it comes to mechanical engineering and design. What we're talking about during today's episode is the design of his bespoke Honda K24 based V8. So this is going to be a 4.8 litre V8. Craig is building this with the intention of it being able to produce around 750 horsepower naturally aspirated, revving all the way to 10,000 RPM. Now we know that the Honda K series cylinder head, as far as 4-cylinder naturally aspirated cylinder heads go, it's pretty much right up the top of my list, but 750 horsepower is still absolutely no joke. If 750 horsepower isn't enough for you though, he's also building it with the intention of being able to add forced induction, and we talk in this episode about the ability to make 1200, maybe 1500 plus horsepower. Another interesting aspect with this engine design is that Craig has been pretty smart with it in terms of the flexibility of being able to mount it into a variety of different chassis. So there's a lot that goes into that. He's lent heavily on Fusion 360 with the design, basically making sure that everything has been built in the virtual world so that before he has a single component actually made and outlays the funds to have those parts made, he's going to have the confidence to know that everything absolutely works. So there's a huge range of topics in here that are going to be perfect for anyone with an interest in the internal workings of an engine and the design of something so bespoke. Before we get into our interview though, I just wanted to mention an Instagram that I put up recently on our HPA 101 Instagram, and this is quite useful for today's topic because it is an engine building topic. We're looking at piston to cylinder wall clearance. Now, there are a lot of clearances inside our engine. All of them are pretty critical. The piston to cylinder wall clearance though is one of the more critical. As its name implies, this is simply the clearance between the outside of our piston skirt and the inside diameter of our cylinder wall. If we don't have sufficient clearance here, what's going to happen is as the piston heats up and expands in operation, is going to end up seizing in the bore. That's not going to end well. On the other hand, if our piston to cylinder wall clearance is too loose, we're going to end up with the piston essentially rattling up and down the bore. That's also going to have the negative aspect that the piston is not going to be well supported, and in turn this is going to affect its life expectancy. It's going to wear, in other words, and it's also going to negatively affect the ring seal. So getting this right is really critical. Now, when we're building our own engines in the home workshop, this isn't an aspect that we physically can control. It's something that is going to be set by our engine machinist. But it is important to, first of all, have the conversation with the engine machinist about what that target clearance needs to be. And then also at HPA, we believe in never making assumptions. So ultimately, once you get all your parts back from the machinist, it is up to the person doing the assembly to check every single clearance and make sure that is correct. And the tool we use for doing this is twofold actually. We start with a micrometer measuring the outside diameter of the piston skirt, and then we use a dial bore gauge, and we zero the dial bore gauge and the micrometer between the two anvils, and then we can use that inside of the bore to measure the piston to cylinder wall clearance. A couple of other aspects we learned from this as well: by checking that piston to cylinder wall clearance at the top, center, and bottom of the bore, as well as in two planes perpendicular to each other. We can also measure the bore for any taper from top to bottom or belling. We can also measure any out of round. So it gives us a lot of information about the condition of our bores and whether they are suitable for our application. And if you are interested in learning more about engine building, this is a skill that is completely within the reach of the average home enthusiast. We do have a range of courses covering engine building topics. We've got our engine building fundamentals course, our practical engine building course, and we've also got a course that will teach you how to correctly degree a cam or performance camshafts, which is one of the more common upgrades we make when building a performance engine. You can find those courses at hpacademy.com/courses. And as an added bonus, as a listener of this podcast, you can use the coupon code podcast75. That will get you $75 off the purchase of your very first HP Academy course. All right, with our introduction out of the way, let's get into our interview with Craig. All right, welcome to the podcast, Craig. Great to have you here. This is an episode that I've personally been really looking forward to recording. I've been following you on Instagram for a while, and I always find your posts really inspiring. So for those who don't know what you're doing on Instagram, can you give us sort of like a brief high-level view of your sort of bespoke engine?
Yeah, so I'm a mechanical engineer, and I've kind of needed to find an outlet and kind of test my skills and abilities as an engineer. I decided to create and design my own custom engine. I started off with, I was going to make a flat 12 engine, but the size constraints of that engine was larger than the CNCs I had access to. And so I switched to a flat plane V8, and then I wanted to make something that was like really awesome and different. I'm kind of bored of seeing so many LS swaps and so many just maybe a 2JZ swap, and it's like 4 engines that dominate the entire car scene. And
it's been played out for sure.
Different. Yeah.
All right. Well, yeah, I'm glad you sort of mentioned your mechanical engineering background. Most people don't wake up one day and sort of think, hey, you know what, I'm going to design from the ground up a custom V8. So that mechanical engineering background, can you sort of talk to us just briefly maybe about what that actually involves in your day-to-day job? Obviously, mechanical engineering can cover a pretty vast amount of ground.
Yeah. So I've actually done a couple of different things with my degree. Prior to my degree, though, I'm super into cars. I started off with an old muscle car, rebuilt it, then engine, designed it, stroked it, and did all that. But so very much mechanic as well. But mechanical engineering started off at a materials company doing something called diffusion bonding. It's where you take 2 dissimilar metals and crush them at high temperatures and pressures until they bond, and it can create some really crazy applications for aerospace, satellites, and things like that. So I was there. Then I switched to a Department of Defense contractor, worked on some composites and some very heavily armored vehicles. I don't know how much I could say about that. And then from there, I actually switched to consumer electronic devices with LTE integration. And I've been designing a lot of plastic housings, docks, and large cycle life plastic components. But automotive has always been my passion. And so I enjoy my work, but I wanted to get back into automotive and doing that again. And so that's why I partially started this project, was to push myself in the automotive sector even more. So
just to be clear as well, this is a passion project, a sideline for you. Obviously, you haven't actually got a commercially viable product to sell yet as well. So you've still got a day job. This is sort of a personal project.
Yeah, it's a personal project. I'm fully self-funded. I have tens of thousands of dollars into this project so far. I still have tens of thousands of dollars to spend to get it to that an actual product viable state. But I've pulled the money aside. I have it all set aside, and this is something that I'm gonna do it. And it might take me a few times. I might have a few coffee block engine tables, but it's going to be something that I will accomplish.
Sure. All right. So a big component of what you've been posting on your Instagram is the 3D models that you've developed for this V8. So where did your skill set with 3D modeling come from? Is that part of your mechanical engineering background, or is that not so much essential and you've developed it yourself?
So it's something that's very critical for a mechanical engineer. You need to be able to use industry standard CAD programs. Generally, the most popular one here in the US is SolidWorks, but I'm also proficient with PTC Creo. I've used ANSYS and a couple other ones. But for this project, I've used Fusion 360. And that was to kind of separate my work stuff and my project stuff completely. So that way there was no possibility of, hey, you designed this on a company computer or anything like that. Gotta keep all that IP and all of that stuff separated. And that's a very important thing if you're ever working on personal projects. Keep that off of your work computer.
That's pretty smart. So, I mean, I don't do any 3D modeling myself. I think I used SolidWorks maybe 15 years ago back in uni for a paper, and that's about the extent of it. But these days we see Fusion 360 is very popular in the hobbyist market, generally because you get cheap or free access to it versus SolidWorks, which is pretty expensive. Like at a high level, the capability of Fusion 360, is there anything sort of that really limits it in comparison to SolidWorks?
So one thing I like about Fusion 360 is every month they basically have an update to it that adds more features and more capability. And when I started this project and switched over to Fusion 360 several years ago, there was some pretty stark differences and limitations. But I would say that gap has decreased significantly, and now it's not as big of a gap. I would say the biggest limitation is flow simulations. Fusion 360 is not as capable. It is just barely adding some of those flow features. Just now, even last month, they added some, but it's still not comparable to SolidWorks, and it's not comparable to ANSYS. And so for those type of simulations, I often have to take it off of Fusion 360 and put it onto a more powerful software for my flow analysis to make sure that I'm getting proper data.
All right. I don't want to dive too deep into this now, and we will come back to it because I want to talk particularly about the CFD aspect. But let's dive a little bit more into this engine and how the idea came to be. You mentioned initially you had ideas behind a flat V12, and you've gone flat plane crank V8 using Honda K series heads. So when you've essentially got a blank sheet of paper in front of you and you're looking at the options available, how did you narrow it down to that particular combination, 4.8 litre V8, flat plane crank, and Honda K series head?
Yeah, so I was very much inspired by a gentleman named John Hartley. He designed the H1 V8. It's a Hayabusa V8. He did it back in, I want to say 2006 or 2007, around that timeline. And then there's a couple of other builders that also are built around the Hayabusa V8, Hayabusa cylinder heads, and have made V8 engines. And I know that could have been done. And I looked at, doing possibly a different motorcycle-based cylinder head, but I felt like that market has been semi-saturated already. Yep. And so then I was like, okay, I need to look at regular production four cylinders. And then it was who makes the best four cylinders. And for me, based on like the flow analysis that I could find and all of that, it seems like Honda makes the best four cylinders, and that can rev really high. And then on top of that, Honda never made a production car V8. They made racing V8s, but they never made a production V8. And I felt like there was a market opportunity there as a possibility if I could pull this off, that there would be a community that would be interested in this outside of, that would be interested in this as like, hey, this is a Honda. I want to have a Honda V8 really bad.
Yeah, absolutely. Yeah, I mean, I can't disagree with what you've said there. I mean, the K series, K20 or K24, in my own experience, I've probably tuned 20, 30 of them, maybe more actually, over my career, and they continue to impress. I mean, as a naturally aspirated engine, it's in my opinion, for a 4-cylinder, that there's just nothing that comes close. Maybe the SR20 VE cylinder head close, but the K series definitely pretty impressive. And I think the other thing you sort of touched on there, that Honda community, I don't know, arguably probably one of the strongest out there as well. So I think that's probably pretty smart. Just to come back to the production car versus motorcycle engine, because you mentioned Hartley, I think that sort of ended up being the basis of the RPE V8 that Radical uses as well, which we actually did a YouTube video on quite a while back. As I understand it, and I haven't really gone too deep into it here, there'd be a couple of advantages with the motorcycle cylinder heads in that motorcycle engines generally are designed to rev higher than automotive car engines. So that's one thing, and I'll get to why I think that's important shortly. The other thing, the design with the Hayabusa engine in particular is modular, which I would imagine from a design and building perspective would make it easier and cheaper. And what I mean by modular is that the barrel assembly is separate to the crankcase and the cylinder head. So when you're building a billet block for the Hayabusa-based V8 or motorcycle-based V8s, that could be much simpler and easier because you're not designing the whole cylinder block as well, the cylinder's walls, I should say. They can just be the production motorcycle barrels. So any sort of thoughts there? I mean, obviously you've gone down this path, but you would have considered this?
Yeah, I actually considered going down a motorcycle barrel assembly design for the V8 with the Honda. It was something that I actually had reached out to John Hartley and emailed him a couple of times back and forth. Hey, this is my idea. What do you think? And he was like, hey, maybe consider this, consider that. And he answered a lot of my questions early on in the project. But for me, one of the things that I know people are going to do with my engine is they're going to boost it, and they're going to boost it all the way to 11. And that's just something that I expect is going to happen. Sure. And in order to have block rigidity and strength, I needed to have webbing across both cylinders, banks, and to strengthen that. And so then it was like, I could make this barrel assembly and it would be cheaper, but if I want it to be really strong and robust and to be able to handle very high horsepower numbers, at least potentially or capable of it, then I should make it a full-blown billet V8 style block that's very stiff. So I feel like naturally aspirated, I could get away with it and I could go with the motorcycle style and the stiffness would be sufficient. But for a boosted application, I didn't want to risk it. And so I pushed for and moved forward with the billet block. Yep. If I have enough orders and there's enough interest, I will do a cast version of my block. Cast versions aren't going to be quite as strong, but I mean, the cast K-series block itself with sleeves is capable of 1,000 horsepower. So a cast block can be very robust. It just, you have to design it and make sure you take all of those considerations in from the beginning.
Yeah, absolutely. I mean, just to come back to that motorcycle barrel style, a lot of these engines, the actual sleeves are not a ductile iron or anything like that. They're a nickel coating on alloy, which then inherently is going to limit the maximum amount of cylinder pressure that the engine can withstand. So that's sort of getting to your point of the strength that you wanted for the boosted application. You've actually gone one step further as well with your billet block. You're using a ductile iron sleeve, I understand. Can you talk to us a little bit about what they are and why you went that path?
Yeah, so a lot of different engines have, they can have, as you said, a spray-on liner that's inside the cylinders, and it'll be a aluminum block, and you just spray this stuff, and it adds a hardness to that cylinder. It makes it so it can handle the piston going up and down quite a bit.
Because you obviously can't run rings against alloy. It's just not going to work. So that's what this coating's for.
Yeah. And it's really amazing. And coating technology in the last 20, 30 years has just been a huge increases in performance and capability. But you're still left with the strength of that aluminum as that circle of aluminum of your cylinder. And so cast iron is significantly stronger and can handle pressures much, much, much higher than aluminum can. Like the Coyote V8 has, I think it's like a 1 millimeter or a 2 millimeter cast iron sleeve that's put into their aluminum block just to give it that extra amount of strength. And Coyote blocks can handle a ton of horsepower right out the bat without having as many issues. My engine is, I'm using Darton mid-sleeve, and so it's a fully water jacketed sleeve, and it's really thick, and it can handle extreme cylinder pressures. So the actual it should be able to handle 2,500 horsepower, the block itself. Then you need to switch to probably a dry sleeve and get the coolant out of there, just for board distortion and all of those sort of considerations you're going to start running into. But yeah,
I think if you've got something that can handle 2,500 horsepower, you probably not too many people are going to be stretching the limits beyond that. So
I don't want people to do that.
I think we're good.
I don't want people. I would like it if people stayed under 1,500 horsepower, and that's my. That's more than plenty, and I feel like 1,200 is even a lot, and I think a lot of people think that they want this 1,000 horsepower mark, but I feel like that's not. I feel like as a community we've been so focused on a horsepower number. The responsiveness and drivability, we're missing the mark.
I couldn't agree more. I coming from a drag racing background where we had a big focus on horsepower for a very good reason. I also see the social media and the print media has played into this a lot over the years as well. You've got young guys just getting into the car scene, and girls for that matter, reading these magazines about 1,000 horsepower street cars or 1,500 horsepower street cars. So it becomes normalized. The reality is they've never probably driven anything with 300 horsepower. And when you've got a small capacity 4-cylinder engine, for example, that genuinely makes 1,000 horsepower, it's going to be a horrible car to drive on the street, I can guarantee. And probably if you built a package that made 500 or 600 horsepower with a better sized turbocharger, a wider power band, it would absolutely destroy the 1,000 horsepower street car on the street. So there's levels to this stuff that people who haven't actually lived through a car at that power level probably don't understand. And there's a million other things we could talk about there, maintenance, etc. But sensible power targets and drivability are something that are so often overlooked in this drive for a big number that you can boast on your social media. Okay, let's just come back a step as well. So you've mentioned that the design of this engine is to use a flat plane crank. Mm-hmm. And I don't get too much into engine design. I've built more than my fair share of engines, but generally we're dealing with whatever the manufacturer had decided from the base design. So flat plane crank, my understanding is there's some inherent disadvantages in terms of harmonics. Can you tell us what the upside of the flat plane crank is and why you decided to go with that?
Yeah, so inherent advantages of a flat plane crank are all of the counterweights and the actual connecting rod journals are in the same plane, and that's why it's called a flat plane crank. And it allows for a much lighter crankshaft than a traditional cross plane crank. A cross plane crank, you're going to have very heavy counterweights. And in order for my engine to have the heavy enough counterweights in my size limitation, I would have to have tungsten slugs pressed into my crankshaft in order to get the weight high enough in order for it to be a cross plane. But another advantage of being a flat plane crank is naturally they can rev higher and faster. But for me, it was to be able to reuse the camshafts. By having a regular 4-cylinder is a flat plane crank. People think it's like this magic statement, but it's like all 4 cylinders are flat plane cranks. And a flat plane V8, I could actually reuse those components of the camshaft and not have to have specialty grinds or a reverse grind for the camshaft.
So just to dive into that a little bit, because it's difficult with a podcast format. We don't have the benefit of some nice graphics to show this. Yeah. But essentially we've got a 4-cylinder engine that has a defined firing order, and the camshafts are ground to obviously suit that firing order when the valves are open and closed. So that works with the flat plane crank because, as you mentioned, a 4-cylinder engine uses a flat plane crank by definition. So when you've got a V8 with a flat plane crank, everything works nicely. So with the cross plane crank, this is going to affect the firing order of your Honda-based V8, which is why you would then need to develop custom camshafts to basically make sure the valves are opening and closing in the correct order for the cross plane.
Yeah, so basically, if I was to run a cross plane crank, I need custom camshafts. By running a flat plane crank, I can use the stock style camshafts. I'm not planning to run stock camshafts, but I can use any aftermarket K series camshafts and be able to run those without any issue. Also, flat plane crank. The most popular manufacturer of that in a production car is Ferrari, and it has a very distinct and unusual sound. And that's why a Ferrari V8 sounds so different than an old muscle car burble and the way they sound. And I really enjoy the sound of a flat plane crank. There are vibration issues that plague flat plane cranks, and I had to spend a lot of time working on those vibrations to make sure that my vibrations were under control for the amount of stroke that I was targeting and the amount of weight of each particular component.
Okay, so in terms of the understanding of this vibration and managing it, so how do you understand what the vibrations are going to be? You've mentioned component weight, stroke, etc. there. So how do you sort of model that and get a real thorough understanding of what vibrations are going to exist in that crankshaft? And then, of course, the follow-up question to that is, how do you manage them so you're not going to end up with component failure due to these vibrations?
So I actually... my daily driver up until recently was a Shelby GT350, which had a flat plane crank. It's the Voodoo engine by Ford. Really fun car. My car was a 2016, and I put about 40-something thousand miles on it, and really enjoyed that. But that car suffered from really bad vibrations, and it vibrated its own oil pump off and loosened it and had massive oil spills 3 times. I nearly burned up that motor three times. Sorry, I was going to swear there. I didn't know if it was appropriate or not.
We'll let you go with it.
And it was something that I was hyper aware of and very sensitive about. And so I targeted that particular engine because that engine is the longest stroke flat plane production V8 that's ever been made in a production car, as far as I'm aware. And at least that was Ford's marketing claims back in the day.
Sure.
And I believe it's either 94 or 95 millimeters. But there's a particular equation that will tell you exactly what your second order vibration will be and the amount of force it will apply in newtons. And so you can...
It sounds like Ford maybe weren't aware of this equation.
They were aware of it. They actually changed the oil pump design, the oil filter, and how it attaches to the block in late 2017. So they fixed it. But the early ones, you had to put on the oil filter and then like crank it on like super hard. Like it wasn't just like, oh, here's like, 20 inch-pounds or however many newtons. But it was like a significant amount of force. And even with that, it still vibrated off. And I was like, it was very frustrating.
Not what you expect from a production vehicle for sure.
No, it's not. And I was very concerned one time because I had gone out to my car and there was this massive puddle underneath my vehicle, and it was I tightened up the oil filter, and I had one of my buddies, and we grabbed 5 quarts of oil, and we put in 5 quarts of oil, and it still needed more. And I was like, how much oil did I dump? It was so bad.
You imagine the warranty claims for Ford for that model year. It must be significant. All right, so you've got this equation, so you can calculate the magnitude of these vibrations, the forces involved, which begs the question: how do you cancel these out and manage them?
Okay, so the main way that most people do it is by having a shorter stroke. The stroke directly affects the magnitude of this second order vibration. And so Ferraris have a very short stroke. I want to say like 87 millimeters. Sure. And I had considered what I could do was go with the K20 and make a K40 V8. Yeah. But I found that if I pulled the weight out as much as possible, I could actually be I could have 15% less second order vibrations than the Ford Voodoo engine with a 99 millimeter stroke.
Okay.
Than the Voodoo with its 94 or 95 millimeter stroke by having components that are basically a third as light. And that was, so it helps you up to a point, and it can get you and help to a certain degree, but there's only so much it can do. Okay. I also have like longer rods, but that's starting to get even more technical. But yeah.
That's good, because I wanted to discuss this, and it feeds nicely into this conversation around the geometry of the engine. And again, you've got a reasonable degree of flexibility when you're designing something bespoke, but of course the Honda cylinder head, to a degree, is going to define your bore center lines, or how far apart the bores are. It's going to limit to a degree your bore diameter. So how did you sort of weigh up bore diameter versus stroke? Because again, we really haven't talked about the 10,000 RPM target that you've got for this engine, which is a bunch higher than Honda ever expected the K series to run. So typical sort of mentality when designing an engine for much higher RPM would be to go with a shorter stroke. And you're talking about 99 millimeter, which is not that. So yeah, talk us around the decisions you had to make there. And then also how that impacts on rod to stroke ratio. We'll probably keep that as a separate topic because that probably needs a little bit of explanation in and of itself. So you would talk to us about your bore versus stroke considerations for a start.
Yeah, so the Honda K series has a 94 millimeter cylinder to cylinder center bore spacing. And that means if I have a 90 millimeter bore and a 90 millimeter bore, so two 90 millimeter pistons, I'm only going to have 4 millimeters of material in between those two pistons in order to keep that combustion pressure all in and held together. That's not a lot of room, and it's actually very small for a V8. Audi uses a 91 millimeter bore-to-bore spacing, but Ferrari uses a 94, but then pretty much like everything else is like 100, 108 millimeters, so a whole lot bigger. So I was very limited on that. And Hondas are also known for their not the best amount of torque. They're not known for having a high amount of torque. I guess they're kind of similar to rotaries in that regard.
Oh, you just triggered a whole bunch of people right there.
I know.
Let's move on. I'm not going to disagree with you.
Rob, Dom, and I have had a couple of chats about that. Fun topic, but definitely a lot of triggered people. So I wanted to have extra torque, and so the way I could get that was by having a longer stroke, and that's why I went with the 99 millimeter of the K24 instead of the K20 with its 86, I want to say, millimeter stroke, which would have been a little easier on my second order vibrations and probably was the more natural choice, but by going with extremely lightweight components, I could get away with the second order vibrations and having it be less than an actual production engine that's making current power and all that.
Okay, so no replacement for displacement there, and you're at 4.8 versus what would be a 4 litre with the conventional K20 geometry. Let's talk about what options exist to get weight out of those components, because you've got obviously a lot of off-the-shelf components available in terms of pistons and rods for the K series. Kind of brings back as well to the conversation about the flat plane crank and the camshafts. Really makes a lot of sense on that topic, because again, massive range of off-the-shelf parts from huge number of aftermarket suppliers for the K series. So people using this engine will be able to benefit from that without needing a bunch of really crazy custom parts. So was this a case of there were already off-the-shelf pistons available that met your criteria, or did everything you designed need to be custom made to get that weight down to the bare minimum?
So in order to hit a 9,000 RPM red line, off-the-shelf pistons and steel rods could be used. Mm-hmm. But I wanted to showcase the maximum potential of my engine and also have it be something that could be driven on the street. And so I'm building a particular engine that I think very few people will spec it out in this particular fashion. So my engine has custom pistons that have been 5-axis CNC'd and have been made ultra light and have had the actual compression distance of the piston moved up, so that way I can have a longer rod. And then my rods are also titanium. And so those two things combined were allowed me to be able to push that RPM red line up to that 10,000 mark. 4Piston is a company, and they've pushed their stroke on their engines all the way up to, I want to say, 102 or 103 4 millimeters of stroke and push it all the way up to 11,000 RPM, which is even higher and crazier. But a normal K24, if you swap out the oil pump on the bottom with an S2000 oil pump, the regular stock engine can handle 9,000 RPMs and be able to do so reliably. Okay. And so with aftermarket pistons, just stock aftermarket pistons and steel rods, my engine will be able to handle 9,000 to 9,500 RPMs very reliably. At least that's my target and goal. And then for my engine, which I'm kind of going the little extra maximum effort, I'm shooting for that 10,000 mark. My math says I can go higher, but I'm trying. I want this to be semi-reliable, so
absolutely
keeping that limited at 10.
In terms of the titanium rods, it's a material that I haven't used in engine construction in the past. What sort of weight difference would you be talking between a conventional steel rod and one made from titanium?
So you could look at a boosted rod for a K series, like actual boosted line of steel rods. Those are around 600 to 620 grams a rod. For an ultra lightweight, naturally aspirated connecting rod, that'll be around 420 grams. And my titanium ones are slightly a little different because I have a larger bearing diameter. I had to do a whole bunch to my crankshaft to make it strong enough to be able to handle stuff. But with my larger bearing diameter, I was still able to hit 380 grams. If I was doing a regular K series, it'd probably be around 340 to 320 grams.
So you're talking a touch over half the weight of a conventional turbocharged suited steel rod.
Yeah, and I could have gone with aluminum rods, and a lot of people did suggest that, but aluminum, as you know, rods have some limitations in fatigue life, and especially for what it is that I want to do with my engine, and that's revving it up and down and going through the entire rev range multiple times, and that's not really the best application for aluminum rods. That rapid change of direction isn't the most ideal.
Yeah, the alloy rods, I think, really still are fairly firmly suited only for drag racing. And at the higher end of the power spectrum, we see teams replacing a full set of rods after 50 to 70 passes. So, for something that's going to see road race application or even daily driven use, yes, there are people using them for daily drivers, but you're kind of walking a bit of a tightrope with the fatigue life limitations there. So that makes sense to stay away from those. This leads me into the next aspect there, which you've sort of touched on already, is this rod to stroke ratio, which I think is probably one of the more overlooked aspects of engine geometry, particularly in the aftermarket. We were just mixing and matching components. So can you talk to us briefly about what rod to stroke ratio actually is and how the rod to stroke ratio affects the ability of the engine to rev and how it produces power and torque?
Yeah, so for my engine and a lot of engines, it affects the amount of vibration and the amount of piston speed. It actually affects a couple of different things. So for me, by having a longer rod, I can reduce the actual amount of vibration in my engine by 5% just by having this extra length to get, hey, I'm pushing that piston up just a little bit higher, so that way it's coming down a little bit and it's moving up and it's not as affected as much. And so that was like a one of my mitigating factors to try and make it so I could hit this higher RPM target, I'd have to pull up my spreadsheet of what the K20 is for its ratio, and then for what the K24 is, and then what I did for my little extra. The regular K24 has 152 millimeter connecting rod length, and then mine is 156 millimeter, and then stroke of 99.
Okay. So, now, one of the effects there with the rod to stroke ratio is that it does affect essentially the dwell at top dead center, and as we go longer on the rod to stroke ratio, or increase the rod to stroke ratio, that increases that dwell time. Obviously, the piston still has the same amount of time to get between top dead center and bottom dead center for a given RPM. That's not going to change, but the way it decelerates towards top dead center and accelerates away is slightly different as the rod to stroke ratio changes or increases. And the advantage with that is it can improve cylinder fill at higher RPMs. That's another consideration you've taken into account here?
Yes, and for those that want to run, I've had a couple of people request an actually shorter stroke than what it is that I have of 99. They want to go 93 millimeters, and instead of changing the deck height of the engine of 231.5 millimeters, but dropping it, but leaving it at that and then going with the longer rod, it would be much more beneficial for those particular applications, and they would be able to get higher RPMs out of it and be able to fill up even more, which then pushes, your components on your cylinder head have to be able to flow at that rate. Like, you can't just say, oh, my engine's going to rev to X number just because. And it's like, no, you have to have every component capable of doing that in order to make it happen. It's only going to rev as high as your weakest link.
Yeah, I think that's something that, again, in the wider enthusiast market is so often overlooked. And the reason I say that is because it's a question I quite regularly field in some of our webinars. Basically, the question is around just increasing the rev limit on the engine. And my answer to that is, to what end? Because if you take your stock engine that revs to 7,000 RPM, that's the rev limit. Well, if you rev it to 9,000 RPM, if the thing doesn't grenade, it's not going to give you an advantage, because if you actually look at the power and torque curve, you're already on the downside of the power and torque by the time you get to the factory rev limit. So by revving it to 9,000 RPM, you're simply going to make less power. So as you say, I mean, it's a knock-on effect. If you want to rev to 10,000 RPM, well, all of the other componentry also has to actually be able to flow. The cylinder head has to be able to support the required airflow. The camshafts have to be optimized for that sort of airflow as well. So yeah, there's a lot more to consider that I think is easy to overlook. And actually brings me to another good question here. We've talked about this 10,000 RPM rev limit, or the ability to rev that far. And particularly when you're naturally aspirated, obviously you can add a turbo to your engine as well. But when you're naturally aspirated, there's only a few sort of levers we have available to pull in terms of achieving a certain target horsepower level. And RPM's a really good multiplier for our torque there. So can you just give us a quick rundown on the relationship between power, torque, and RPM, and really why the high RPM number is so important to that equation?
I think you'd be better at explaining that than me. Honestly, you've gone over it so many times in multiple of your videos. But basically, because I'm limited on the amount of displacement I have. So in order to make more power, I have to go higher up in the RPM, and to get higher in order to make that actually happen. That's why F1 engines rev up so high. I mean, the old V10s revved up to 20 grand. I mean, just absolutely insane. And it's because they had such small displacement. They were making up for that lack of displacement by revving the engine higher. For me, I have to go with titanium valves and this ultra CNC'd head that's like at the very max limit of what you can do with a stock casting in order to get up to that RPM. And then I have to have a special camshaft that's designed for those lift considerations. And then I have to make sure that my engine, the piston to valve clearance is very tight. And I have to triple check and make sure that everything is perfect, because at that high of an RPM, things also flex and move around. And so you have to reduce that valve train flex. And so the actual camshafts need to be made out of a stronger material. And it's just a knock-on effect. And
I think all of these things that again, for the average enthusiast out there, you just don't ever consider this, but these are the considerations and the difficulties when you're trying to make a lot of power from a small capacity engine. And just to bring you back to the F1 sort of comparison that you made there, I don't really remember the capacity, maybe 3.5 and then 3 litre when they were V10. And the final, I think they got down to 2.4 litre V8 before this current crop of hybrid garbage. But not a fan, sorry.
It's okay. I'm not a fan of the sound at all either.
No, I don't think too many people are getting barred up about that. The 2.4 litre though, I mean, if we compare that to a conventional automotive engine that we're more familiar with, like the sort of line in the sand was always 100 horsepower per litre. And I mean now, Honda K series, maybe 150 horsepower per litre is probably not insurmountable. A challenge, but not insurmountable. But then we've got these 2.4 litre engines in F1 revving, I think, don't quote me, maybe 18,000 at that point, and making, who do you want to believe, 750 to maybe 900 horsepower, again, depending on what spec you want to believe. So just massive horsepower per litre. But what again is easy to overlook when we're looking at these numbers is, great, but we've got an engine that probably idles at 4,000 to 5,000 RPM and probably doesn't make any power that's usable at all below 15 or 16,000 RPM. And that's the part that we need to understand. Everything in that engine is optimized for that tiny little rev range where the engine actually works. And then we've got technology like pneumatic valve train, which is unattainable for us in the passenger car sort of world. So bringing it back to something a little bit more manageable, 10,000 RPM, we don't need anything like pneumatic valve springs, but you do, and I'm not sure how much of this you're using. One of the really nice advantages with Honda with their K series is we've got two technologies that work nicely in our favor. We've got their VTEC, which is nothing new, where we've got a low RPM optimized cam profile and a high RPM optimized cam profile. And then their iVTEC, which is just continuously variable cam control on the inlet. So a lot of technology to really optimize the valve train operation so that we can kind of have our cake and eat it, the best of both worlds. We've got good low RPM performance and torque, which you've already kind of alluded to, but we're not compromising the high RPM performance, which would have to choose one of those two compromises if you were on a fixed cam profile. So I assume you are still using the VTEC system. Are you also using the continuously variable cam control, or are you too tight on valve to piston clearance to really get much out of that?
I have to reduce it. I think it's down to 25 degrees of variability on my cam. Some of the iVTEC, it's like, I want to say 40 degrees. So I'm reduced at my amount that I can do. But I have to have VTEC. There's a Honda, and I think the Honda community would murder me if I did not have regular VTEC as well. So
but that is an advantage to you anyway, yes. Isn't it? On all of the aspects I just mentioned.
Yes, and I want this engine to be streetable for myself. And if it was just purely a race engine, I would probably eliminate VTEC and go with the VTEC killer setup and just go for that ultra number of high performance and just try and hit that peak number. But I want drivability and that high RPM. So I'm going for kind of the limit of what is both streetable and the high RPM. So it's like a stage 4 cam. And then stage 5 is when they cut off the actual, all the other lobes and just stick with the VTEC lobes.
Yep. Okay. Now, you've also mentioned in passing here the strength of the crankshaft, and I just want to dive into this. I think I remember reading one of your Instagram posts about this, but again, often overlooked aspect of the strength of the crankshaft. A lot of this is dictated by the overlap between the main bearing journal and the connecting rod journal, and that's given you a few complexities with this engine. Can you talk us through what the problem is there and how you've overcome it?
Yeah, so it was actually a big pain spot for me in designing this engine. So with the K24 and a normal 4-cylinder, you have a lot of meat in between one main bearing and then the next main bearing. So you have a lot of room in there. So its 94 millimeter bore spacing doesn't really negatively affect it. And its crankshaft bearing overlap area is only 18 millimeters squared. So that main bearing to the rod bearing, that overlap area is only 18 millimeters squared.
Again, this is something that's difficult to visualize without the benefit of some pictures. So just to try and sort of describe in a bit more detail what you're talking about there, if we take a cross section vertically through the crankshaft, what you're talking about is if you look at the rod journal, that's a circle, and that overlaps with the main bearing journal. So it's that overlap of material you're talking about there was 18 millimeters squared. Is that what you said?
That is correct.
Okay. We're just trying our very best to kind of explain what we're talking about here without the benefit of visuals.
You did an excellent job, much better than me. And so for me, that just would not fly. Once you put in another set of connecting rods in that exact same space of 94 millimeters, you have no room. And you need to still have strength in the crankshaft to be able to handle potentially boost and these high horsepower, naturally aspirated things. And so I actually had to change the bearings on my engine. My bearings are not Honda. Well, I have main bearings from a Lamborghini. It sounds a little crazy, but it's actually don't tell anyone. But it's actually the same as an Audi R8, which is the same as their 4.2 liter that was in their B5. They use this because their bore spacing was so tight on both their V8 and their V10. They have very thin main bearings, but that are very large. I want to say it's 67 millimeters. And so that's versus Honda, which is only 55 millimeters. That extra 12 millimeters is huge. Mm-hmm. And then I switched from the K series rod journal size of 50 millimeters to the actual J35, which I believe is 60 millimeters.
So you've gone larger in the main bearing diameter or main journal diameter and also larger in the big end diameter. So you've basically increased the overlap on both sides.
Yeah. And so now I went from 18 millimeters squared to 272 or 275 millimeters squared. And
that's massive.
So it's a big difference. And that allows me to get much closer in strength to the targets I'm hitting. Sure. A regular LS3 V8 is 200 millimeters squared is what they have. An actual like Voodoo V8 is around 370. So even at my 272, there's still more engines that have even more overlap. But I'm limited by the bearing speed at this point now, because if I go larger than this, I have bearing speed issues, and so
bearing speed issue. That's something I haven't really given much consideration to. So just talk us through sort of what that term means should be pretty self-explanatory, but what it term means and where that bearing speed limit comes from, what defines that?
Okay, so a bearing speed is basically the amount of surface area of the bearing and that is rotating about an axis. So if you have, let's say, a 10 millimeter, or you could even think of like a turbocharger's shaft, and that'll spin at incredibly high RPMs, and it's not going to explode. But like if you spun those exact same numbers on a V8, it would immediately grenade itself. And it's because of the amount of surface area that's being moving around the object, that surface area. And so you can, it moves up exponentially. As you have a very small shaft, you can spin it much faster than a very large, thick shaft. Then you're limited on the amount of speed you can put in. And so the bearings that I actually have are very high performance bearings from King that have specialty coatings. And then I'm actually sending them off to another shop to have them have another coating put on top of that, just to reduce make sure that the bearings will live at the RPM targets that I'm saying that my engine should be able to handle.
Yeah. Okay.
And so that was extremely critical. So finding high performance bearings that could handle the RPM, and then working with King to make sure that the RPMs I was suggesting and wanting to do were actually possible.
Yeah. Yeah. All right. I want to move on and talk about probably one of the more hotly debated topics that I see people questioning about, pun completely intended there, which is your hot V configuration with this V8. So hot V, the exhaust manifolds are in seemingly an unconventional position in the middle of the V in the valley, where in a lot of applications we see the intake manifold more conventionally there. But hot V is certainly not unique. You haven't invented it. But can you talk to us about why you are forced down this path, and maybe pros and cons of hot V versus a conventional V?
Yeah, so as you said, I was forced down this path, and that's one thing I get so many questions about is why is the exhaust in the center? Why is it in the center? You should switch it. You should switch it. And it's like,
I had answered this.
Eh? Yeah, I didn't think about this one. It was actually a major pain point. So I've been working on this project for the last 5 years, roughly. And in my free time and in my time that's kind of like forced, but basically the timing chain tensioner on the K series and its location, once you switch it over to V8, ends up a dead center on the main block and the girdle with the bottom end of the engine. It ends up right in between those two locations, and then it ends up right in the middle of the engine's like main bearing studs. And so it's like, this is basically, there are ways I could have possibly gotten around it. I looked at switching to a Mazda timing chain tensioner, or to VW one, and the one that was hydraulic, that was like gas assisted instead of being oil driven. And I looked at all of these different options, but I kept running into hitting and being on the actual parting line of the block, and also running into the main studs of the engine. And it was almost, I almost quit the project. I actually stepped away from it for like 6 months, and I had already bought like an engine that I 3D scanned, and I had already like put all this effort into it, and I had spent so much time. And then I was like, well, let's switch it to a hot V. I remembered going to Barrett-Jackson when I was like, I don't know, 2004-ish, and I saw this Ford Falcon that had a hot V engine. I was like, this looks so cool. It's like all the exhaust tubes in the center, and it came out the front and it went down under the car. It was a really cool design. And Indy cars back in the day, they were hot Vs, and a lot of modern turbocharged V8 engines are now hot Vs, and some V6s are also switching to it as well.
You see it quite commonly, I think, with some of the European V8 twin turbo engines. That the hot V is just the way they've gone.
So even Ford, their diesels, their Power Stroke diesels, are hot Vs, and Cadillac, they have a hot V, and then all the German V8s, turbocharged, Porsche, Audi, Mercedes, BMW, they are all hot Vs. So this is something that's unconventional, but is becoming more conventional. Even Toyota is about to release a hot V engine, and it's really nice for packaging of a turbocharger on top of your engine. Basically, by having a hot V, you can mount your turbochargers inside the valley of the engine. And then by having them mounted inside the valley of the engine, inside that V, you can have an extremely short intercooler or turbocharger to intake piping that is very short and extremely compact. And it reduces your lag and improves the responsiveness of the engine. Mercedes, they caught a lot of flack when they switched from the M156, their, C63 V8 engine, really awesome and amazing one, and then switched to their new engine, which was a hot V engine. But my wife had that car, the W205 C63, and that car, you could barely tell that it was turbocharged. Its response to the throttle was so fast and so quick. So it makes a lot of sense for turbocharged applications. And I believe most of my builds most of them will probably go down that turbocharger route, either eventually or at some point. And I think that'll be a very common thing for the people that are interested in my engine. And so it makes a lot of sense for that. And since I was forced down that direction, it's okay. And then for a naturally aspirated V8, it doesn't make as much sense because the exhaust manifold gets a little crazy and it's a bundle of snakes. But it will have a distinct sound and it will have a distinct look that will help it stand apart.
Yeah, definitely. It's maybe not going to be for everyone. The fabricators are probably going to hate it, particularly naturally aspirated. But as you say, I mean, your hand was forced, so it kind of is what it is. One last point on that, which has been picked up on a number of times that I've seen as well, is obviously heat management does become a consideration. You're not worried about that? How you view circumventing issues there?
Yeah, so a lot of hot V engines, especially some of the earlier ones, like the BMW N63, had issues with heat management, and they would cook their valve cover gaskets. It was just a matter of time. It wasn't if, it was just when. And so for me, what I'm doing is I'm doing a more modern style heat shielding that is press fit and is stainless steel with a thermal insulation and then stainless steel. And it's this like dimple dye thing, and that is then formed onto the exhaust manifold itself. And that keeps and retains the heat inside of there. And it actually improves your turbocharger response times as well. So it's beneficial. You can also ceramic coat it and do that, but generally that's not as necessary. But this new style of heat shielding is very powerful and much more capable than, say, even like a titanium wrap or ceramic.
Yeah, I think it's fair to say that heat our shielding and thermal management products have come a long way. And there's been a lot that's also been developed for professional motorsport and OE applications that you've now got access to. So I think with the right management, and it does need some consideration, but the right management, it really is an issue. Look, Craig, I've got probably about another hour worth of questions I could ask you. I feel like we've just scratched the surface here, but we're probably getting a little bit long here, and I do also want to respect your time as well. I think what we'd probably like to do is simply have you back as a guest again, maybe once you've got the engine a little further along and maybe up and running, and we can work out sort of how the validation of the project came out and whether you hit your numbers and how everything's working out. So I think we'll finish up with a couple of last questions, and the first of those is, if you sort of looking at the point you're at now in your professional career and what you're doing, if you were to give advice to a younger version of yourself in terms of how to fast track your career and where you've got to, what advice would you give?
I've had a lot of different engineers reach out to me that are young and in college, and my recommendation is always this: create a personal portfolio of yourself, of your personal passion projects that you're working on, and showcase that you can do things in CAD, and then create also some mathematical analysis of whatever part you're designing, whether it's a Nerf gun or whether it's like a mouse. Use some simulation and create this brand of yourself as being capable of understanding materials, being able to use CAD, and to use simulation, and that those three things dictate your engineering process, and that you can showcase your failures and your successes, because that altogether is what engineering is all about. Engineering is just fancy problem solving. Sure. And that's it.
Yeah, it makes a lot of sense.
And so I think I would just showcase some of that even more than what I did in college.
Yeah, I think that speaks volumes to a potential employer, particularly if you're trying to get into the motorsport side of mechanical engineering and design. Having that personal portfolio and being able to show a potential employer, this is my skill set, that speaks volumes, and it's going to be a very powerful CV, I believe. And last question for today, Craig: if people do want to follow you, if they've been hiding under a rock and they haven't seen your work so far, where can they find you?
I'm on Instagram, and that's my main area. I'm under Neutron Engines, and I post pretty much everything. I'm an open book. I showcase some of my successes, some of my failures, and some of my challenges. And if you want to find me, you can find me on Neutron Engines, and I'll show basically the whole engine design process and talk about each part of it as I go along.
There's a huge amount of information in there for those who are wanting to dig into your older posts, and I also respect the fact that you seem to put in a lot of effort to answer the questions you get, and there are a lot of questions. I know from our own Instagram account that's a lot of work, so respect there. Look, Craig, really, it's been a great interview, and really interesting to get some more insight into the development of your V8. We cannot wait to see how it goes once it hits the dyno and the racetrack. So we wish you all the best and look forward to catching up again soon.
Thank you, Andre. I appreciate it, and I look forward to chatting with you again. And hopefully it's not about a table, and it's about a well-running engine. And maybe it'll be at PRI or some other locations, and we'll see where it goes from here.
Look forward to it. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.